we are very pleased to have Dr. Jorge Marques from MIT Will Oliver's group at MIT. I met him during my visit in summer, and at that time he's one of the hosts that I was arranged to meet, and he introduced a lot of his previous work and also including his current work using Physonian to build up the multi-qubit device, which is also very fancy. So a short introduction to George's background. He got his PhD from TU Delft with Professor Leo Di Carlo, who is also one of the leading pioneer group in superconducting qubit. And he did his thesis on a distant 2 surface code QEC, which is sort of the minimum of the QEC scheme, because you need to create a square getting larger and larger. In order to have a square, start with 2 by 2. So we call it distant 2 surface code QEC scheme. And then this field is moving fast. He just told me he did this in 2020. And at the 2022, Andrea Waraf group, they demonstrate the distant 3, which is 3 by 3, which is 9 qubit, data qubit 3 by 3, surface code, and published in Nature. And last year, 2023, Google Quantum AI demonstrated the distant 5. So it's a 5 by 5, 25 qubit, surface code QED published in Nature as well. And this year, in August, Google Quantum AI released distant 7, surface code QED in archive. So we see this progress a lot, and we are also, we are trying to build up a logical qubit, which is sort of, has a very high gate fidelity and the long coherence time. So I'm very happy to meet George in MIT, and he has background in this, and probably he can give us a lot of introduction, because I believe many people are not in this field. So let's welcome George for this talk. Okay.
All right.
You can. It's all yours. Yeah.
All right. Yeah. Thank you very much, Quillen. Happy to be here. Yeah. So I'm working at MIT now, but the work that I'm presenting today was actually done in my PhD in Delft, in the group of Leo Di Carlo. So I'd be remiss if I didn't acknowledge my experimental team that took part in this research, as well as our theory collaborators, both from TU Delft and River Lane. So yeah, let's get started. So the outline of this talk is basically 2 experiments that I'll talk about. The first one was a distance 2 surface code that we published back in 2022. And the second one is a more involved experiment where we grew that code to a fully protected distance 3 surface code. Yeah, also feel free to stop for questions throughout the talk. I'm happy to answer or give more details if you want. So let's give a brief introduction to quantum error correction. So why would you ever want to do quantum error correction? Well, if you look at the state of the art in quantum computing platforms, you get single qubit gate errors that are about 10 to the 5, and 2 qubit gate errors that are about 10 to the minus 3. And what you actually need for useful quantum algorithms is error rates that are much, much lower than that, right? So we're looking at things like 10 to the minus 12 for useful applications. So under the assumption that making more qubits is easier than making them better, then quantum error correction is a viable path for a low error logical qubit. So what does this mean? We're going to take a single noisy physical qubit that is prone to errors. We're going to add a bunch of them together, turn them into a logical qubit that's hopefully less noisy. And if the physical error rate of these qubits is lower than a certain threshold, then you can show, and in fact it's been demonstrated quite robustly this year by Google, that your logical error rate can be made arbitrarily small by scaling your code distance or the number of physical qubits. So how do we do that? How do we actually encode a logical qubit? So the formalism that we use is called stabilizer codes. And the idea is that you have a single physical qubit that's has a subspace of dimension 2. You bring many of them together, so you end up with a subspace that has a dimension of 2 to the n, but you somehow want to live in the subspace of a single logical qubit that's dimension 2 again. The framework with which you do this is the stabilizer framework. And this is just a set of commuting observables, for example, Pauli matrices, whose common eigenstates will define the logical qubit subspace. So the idea is that you're going to choose these observables in a clever way, such that the common eigenstate of all those observables leaves the remaining qubit degree of freedom non-local throughout the code. An example of this is the distance to surface code, which we'll talk about. So this distance, it's an array, a 2x2 array of physical qubits right here. And since you have 4 physical qubits to collapse it into a single logical qubit, you need 3 stabilizers. The stabilizers are denoted by these plaquettes. They're green if the stabilizer is a Z-type stabilizer, or blue if it's an X-type stabilizer. So if you take these 3, which all commute with each other, and you restrict your subspace to common eigensubspaces plus 1 of these stabilizers, you'll end up with a subspace that's generated by these 2 states. If these are just GHZ states, if you wish, of different 2 superpositions. If you call this the 0 logical state and this the 1, then you're automatically defining a Z logical operator. Now it's important that this logical operator also commutes with your stabilizer set, because we want to measure stabilizers without destroying this information. And then you find your X logical operator by just finding an operator that has Pauli algebras. That is, they anti-commute with each other. And in the surface code, these operators are spread non-locally throughout the lattice. In the way that we're showing here, Z operators are always going to be shown horizontal throughout the code, and X operators are always going to be shown vertically.
I have one question here. Here.
Go ahead.
For your logical state, the 0 arrow and the 1 arrow, is this the only choice, or do you have other choice that you can have?
No, there's freedom in choosing these. These are the states that respect +1 eigenvalue of all these stabilizers, but there's no reason why you can choose a certain combination of these states. The choice is really up to you. It's arbitrary.
Okay, I see. Yeah. Okay.
All right.
Okay.
Yeah.
Sorry, but
yeah, go ahead.
The states are arbitrary, but the subspace is not, right? Or even the subspace is arbitrary.
Well, let me think. So there's
I think once you fix your stabilizer,
2 to the 3.
Once you fix your stabilizer, the encoding subspace is fixed. But of course, that this 2-dimensional subspace, that you have freedom to choose the basis inside these 2-dimensional subspaces.
Yeah. In general, there's 2 to the 3 subspaces that you can work with, which are just the combinations of zeros and ones. Whether that is arbitrary, I'm actually not sure. They have to be states that are non-local. So these subspaces, like I forgot who said this, but I think the subspace is arbitrary, but the generators of the subspace are not, maybe.
Okay. Thank you.
Yeah. So, anyways, so these stabilizer observables are the things that we're gonna want to measure throughout our experiment, right? Those are the things that are gonna project us into the code subspace. And the way we do this is by means of a parity check. So we're gonna introduce an extra ancilla qubit per stabilizer that we have. And we're going to use that Logical-qubit with this simple circuit right here to map out the parity of the data qubits onto the Logical-qubit so it can be read out without you interfering with your data qubit state. And how can we use this for error correction? Well, the idea is that if you start in a product state that's not necessarily one of your logical states, you measure a round of stabilizers, right? And you're going to be projected into your code space. Say you're projected into the logical 0, right? If you keep measuring your stabilizers, you know that ideally your stabilizers are all going to be correlated and they're all going to be +1 if no errors occurs. When an error does occur, say for instance a Z error on this state, it will basically flip the sign of this state, and if all goes well with the stabilizer measurement, you're going to detect it as a change of parity right here. And then you'll know that the state that you have is not your logical state anymore. So at this point, you don't know where this error occurred, but you can just choose to throw out data where this happens. And you can restrict the analysis of data in your experiments to +1 eigenvalues of stabilizers in all your stabilizer rounds. So to give a brief overview of our quantum hardware that we'll use for these experiments, it's a pretty
I have also a very quick question to interrupt.
Go ahead, Quay.
Yeah, this parity check, if one error happen, parity will change. But the reason that you don't consider 2 errors happen at the same time, it's just the chance is very low. Is that correct?
Right. Yeah. So indeed, 2 errors can happen, and that probability will be, if probability from 1 error to occur is p, then that probability is p squared. So ideally, that will be lower.
I see.
Of course, it can still happen, and they can still lead to logical errors. Mm-hmm. As you grow your code distance, you can also start correcting for higher distance errors as well, and you'll start suppressing those well. And the idea is that as you increase your distance, those errors are going to become, the errors that you can correct are going to become lower and lower in probability.
Mm-hmm. I see. Okay, thanks.
Yeah, no problem. So yeah, like I said, our quantum hardware is pretty vanilla circuit QED hardware. So we use a flux tunable transmon circuit. It's a loop of Josephson junctions that you can use to effectively tune the EJ near Hamiltonian, and a capacitor right here. This is a transmon Hamiltonian right here, and you can think of it as wave functions in this superconducting phase subspace in this this superconducting phase potential. And if your EJ is much higher than your EC right here, then all your wave functions are going to be bound into this well potential, and they're going to look a lot like a harmonic oscillator, at least for the first few states in this. So you can model it as basically a harmonic oscillator with a little bit of a nonlinear term. This is what it actually looks like on the device. It's just 2 capacitors right here, and this width is here. You can see it. There's a bias line, so you can run DC current to bias your loop. And then there's just capacitors for you to couple to other stuff. We'll see what they are. So our 2 qubit gates are mediated by charge coupling between qubits. So it's basically effectively a capacitance coupling. It gets you this coupling term J and N right here. And what this will do is introduce an exchange interaction that will generate avoided crossings. Now we use this for 2 qubit gates by specifically leveraging this avoided crossing of the 1-1 state. We're gonna flux bias the high frequency qubit through this avoided crossing, and by using some clever Landau-Zinner physics, we end up with a pi phase shift on the 1-1 state alone, which will implement the CZ. This is what 2 of these qubits look like on the device. So they have a CPW, but it really effectively just implements a charge coupling between the qubits. Now for state readout, again, pretty simple stuff. We have a readout resonator that's coupled to our qubit. It's dispersively coupled so that the frequency is far detuned from the qubit frequency, and you can write your Hamiltonian as basically two lamp shifted resonators with your qubit and your resonator and a dispersive shift. And then by probing the scattered signal from the resonator, you can effectively read out your qubit without demolishing it. So that's it. So the full chip is right here. We use multiple feed lines where we couple several resonators here in blue for multiplex readout, so we can be more efficient in the way we do readout. And yeah, each qubit has a dedicated drive line for charge driving the qubit, a flux line for DC bias and some baseband flux pulses for the 2 qubit gate physics. And then there's readout resonators. Like I said, there's a little bit of a nuance that I skipped, which is this Purcell filter right here that just protects your qubit from Purcell decay into this lossy feed line environment right here. So yeah, that's it for the quantum hardware. Any questions here? All right, if not, let's get started. So how are we going to use this for this initialize states in this distance 2 surface code? So we start by initializing an eigenstate of one of the stabilizers. Say, for instance, the 0, 0, 0 state is an eigenstate of the Z stabilizers. So then you can measure those Z stabilizers to detect whether you've made any errors in the preparation of this state. Okay. And then by measuring the X stabilizers, you're going to collapse the 0, 0 state into your logical state 0 right here. Now, if we can do a pretty analogous procedure for X basis states, where instead of initializing in all zeros, initialize in all plus or in all minus to get the plus logical states. So how do we, how well do we prepare these states? Well, after doing this, we do data qubit tomography. We do full tomography of the 4 data qubit states.
I have one question here. For the first row, for the first row you mentioned here, you say you first perform the Z stabilizer, which is understandable. You measure the parity, and for the second one, you measure the X stabilizer.
Right.
But in usual case, I would imagine that you sort of prepare the state into the initial state was in the equator of the Bloch sphere. Then you kind of rotate it back to Z, and you do the X stabilizer measurement and rotate it back to I mean, here the X stabilizer just working as a sort of the changing the basis. Is not actually measure the X stabilizer. Is it correct? Because when you measure the X stabilizer, it can still give you 1 or minus 1. This kind of eigenvalue usually, right?
Right. So in this state, this product state is an eigenstate of this stabilizer, but not of X.
Yes.
Right? So what happens is that this measurement outcome will be random. I think that's what you're saying, right?
Mm-hmm.
So what we do is, if it's +1, we keep the data. If it's -1, we throw it away. So we know straight away that we're throwing half of our data away just because we want the even parity state of this stabilizer. I don't know if that answers your question.
Yeah. Okay. Anyway, my understanding is that you want to create a logical state by this method. I just like usually when we say the measure the X stabilizer, that still give you an eigenvalue, 1 or 2. But here you use it as an operator to create the logical state. That's what I understand here.
Right. Yeah, that's correct. So the idea is that even if you don't start, so it's hard to start in a GAZ state, right?
Yeah. For example, if you start with your qubit state at a plus, right, plus or minus, and when you conduct the X stabilizer, that should give you an eigenvalue of 1 or -1.
Right.
That's right. But here, yeah.
In this case, you'll get all the X stabilizer, being all +1, and you can use that to detect initialization errors.
Yeah. I see. Yeah, the second row is what I meant. Yeah. I see.
Yeah.
Okay. Sure. Okay.
All right.
Go ahead. Yeah.
And yeah, we can do full tomography of these states and look at the fidelity of these target states, and they're going to be anywhere from 90% to 85%, maybe a little bit higher for some states. But you can also ask the question, well, what if in a following round of stabilizer measurements we could detect all weight 1 errors, right? and just take the penalty of errors that are within your code subspace, and that gives us the logical fidelity right here. So if essentially we're taking that full physical density matrix and collapsing it into the logical subspace. And if we do that, we see that we actually have very few errors, which means that most of our errors are weight 1 and can be found in later rounds, provided we do our stabilizer measurements well. So that's it for logical initialization. So what we can ask now is, how are we going to measure our logical qubit? And in the surface code, you can do Z and X type measurements fault tolerantly. And the reason why that is because you can measure simultaneously your logical operator, shown right here in these 2 qubits, and the remaining qubits to measure the relevant stabilizers for that measurement. So for instance, when you're measuring the Z logical operator, you can measure simultaneously these 2 observables, Z1 and Z3, right here, this stabilizer and this, which allows you to do, it allows your measurement to also be protected against weight 1 measurement errors. Same goes for your X logical operator. Unfortunately, for the surface code, you can't do a logical Y measurement fault tolerantly, because there's no way you can construct all your relevant stabilizers while also measuring this operator right here. But you can measure one of the stabilizers and make sure that at least this qubit right here is protected against weight 1 measurement errors. And we could just measure standard cardinal states, for instance, the ones that we prepared in the previous slide. But we wanted to use this to do full tomography of our logical subspace. So we wanted to prepare some interesting states. So we use this procedure to prepare arbitrary logical states. And in here, alluding to the point that me and Kuei Lin discussed before, you're not in an eigenstate necessarily of either one of these stabilizers. So that's why it's not fault tolerant. You can't use any of the stabilizers to detect initialization errors, right? Nonetheless, you can create arbitrary logical states right here, and we can sweep one of these angles to rotate your logical qubit around one axis of the Bloch sphere and the other one around another axis. And that's what we did. So we prepared states around the X, Y, and ZX planes of the Bloch sphere, and you can look at the expectation values of all the 3 measurements right here. And the interesting thing is, like you'd expect, the logical Y measurement curves always have lower contrast than the Z and X curves, just because they're non-fault tolerant and they're vulnerable against weight 1 measurement errors right here. So yeah. Any questions?
Yes, I do have a question. This part is actually the most confusing part to me when I read the paper.
Mm-hmm. Okay.
So the logical gate here is defined as Z arrow and the X arrow, right? And they are the logical qubit state is the eigenstate of this Z arrow and the X arrow. Is that correct?
Sorry, I don't think I understood that.
Sure.
Could you repeat?
Sure. My question is that as follow the Z arrow and the X arrow. What are the purpose to have these two gate? These two gate do what? They operate.
Oh, these two right here.
Mm-hmm.
So these just yeah, these just make it such that your initial product state lands you in the logical subspace along a specified direction in your block sphere. And I don't know if there's an intuitive way of seeing that, but what I can tell you is that this theta angle right here will directly control the angle in the ZX plane, and the phi angle right here of this gate will control the phi angle around the XY plane of the block sphere.
So let me establish a few things. So the X arrow and Z arrow, I mean, for the logical state that you just mentioned, this 0, 0, 0 plus 1, 1, 1, 1, this logical state is the eigenstate of this Z arrow. Is it correct?
Yeah, that's
okay.
correct.
That's correct. Okay. So the question is that why we need this Z arrow and the X arrow? Why we want to do this?
Yeah. So those. So you could initial. I think I understand your question. So you're saying we could initialize, for instance, in a plus state and rotate it afterwards. Is that your point?
It's simple. Is that why we choose this Z arrow and the X arrow? Just because they are the logical state is the eigenstate of these two operators. So we use this operator to know whether the logical state is good or not. Is that the purpose of doing this? That's my question. Because you are trying to find an operator which make the logical state the eigenstate of this operator, and then you use this operator to verify your logical state is good or not.
Oh, right. Yeah. No, yeah, that's the purpose. That's the purpose.
Okay,
so
I see.
The idea is to. No, sorry, it took me a while to get there. I'm sorry about that. Yeah, it may seem a bit dumb, but the idea is just to go from doing things on a single physical qubit level to just operate your qubit as you would do in a quantum error correction setting, right? To operate your qubit as a logical only based on logical operations. That's the whole idea.
Because I do know, like in Warner's paper, they do the fidelity of this gate, logical gate, which is XL and the ZL. And that's the reason they do this, because you use logic state to sort of verify whether this gate it's good or not. So they choose this method. Okay, if what I say is correct, that would be helpful, because that will sort of initially confuse me, like why we are interested in this Z arrow and the X arrow. They are along the edge, and what do they do? But if it's just to verify your logical state, that can help to have a good gate fidelity, and that's a good reason to do so. That's my question.
Yeah. No, it's to verify and also make sure your measurement is fault tolerant. To see that one measurement error doesn't propagate, doesn't give rise to a logical error.
Okay. But you haven't talked about error correction yet, right?
No. Yeah. So we're not going to do error correction in this code. Only in the following one. We're still only doing error detection.
Okay. Okay. Good. Okay. Thanks. Yeah. Please go ahead.
Yeah. No worries.
Yeah.
Yep. I think. All right. So yeah, fine. We've done state initialization, and we've also measured our states. The only thing left to do is to do gates. So we're gonna do a set of transversal and therefore fault tolerant gates. These are just your normal surface code operators. The reason why being transversal, so transversal means that you can do them basically just using single qubit operations. And the reason why these are fault tolerant is because no one single qubit error can propagate into many or propagate into a logical error. So these are the only two gates that you can do like this in this code. Now, if you wanted to do arbitrary gates, like a universal gate set for this logical qubit, you would need non-Clifford gates, right? You need something like a T gate, for instance. And to do this, we've used this trick of injecting a non-Clifford state from our ancilla directly onto our logical qubits right here. So these are, again, non-Clifford gates. We can control their angle by the angle of this ancillar rotation right here. But these are not going to be fault tolerant, so they're going to have a lot more error. So how are we going to benchmark them? So the idea is we're going to do process tomography of these gates, but again, in a logical qubit setting. So we first initialize in one of the 6 cardinal states right here. We're then gonna do tomography of the input logical state. We're gonna, and of course we get the density matrix, the logical density matrix of the input states right here. We're gonna run our gate and then do another round of error detection to detect errors that might happen during the gate. We did this for the T gate, for instance, right here. These are the output states that you get. So the T gate is a 45-degree rotation around the around the z-axis of the block sphere. So plus goes into this tilted state right here. Same for the plus I state. So with this information, we can construct a Pauli transfer matrix for the gates, right? So basically, we can do process tomography of our gate, and we can compute a gate fidelity from this. So we did this for the 2 fault tolerant gates right here, Z pi and X pi. Using this non-Clifford procedure, we did an X pi over 2 rotation, and using this procedure right here, we did a T gate. And with this set of gates, you basically have a universal gate set for a single physical qubit, for a single logical qubit, of course. We can look at their fidelities. Their fidelities are not so bad, actually. So they go from anywhere from 98 to 96-ish% right here. Of course, the states with the highest error are the non-Clifford gates right here. And again, the purpose of the experiment is just show that we can manipulate a logical qubit only using logical operations at the logical level. And finally,
for a previous page, what is the R arrow in the middle means? Sorry, I missed this part. This R arrow you highlighted with yellow color. R arrow in the this one. Yeah.
Oh yeah, this is your gate, the logical rotation.
Logical rotation. Okay.
Yeah. So you go from a product state to measuring your stabilizers and landing in a logical state. You do your logical gate, another round of stabilizers to detect errors, and again measure your output states.
Logical rotation. Okay. It's a similar to a physical qubit. This kind of rotation, but just in the logical qubit space.
At the logical level. Yeah, exactly.
Okay, I see. Got it. Okay.
Sorry, just to clarify, because I heard you said before when you prepared these cardinal states, it's in like the non-logical sort of space, right? But you're doing the process tomography logically. Is that right? Or are you doing everything without the logical and then sort of reinterpreting it at the logical level?
No, so the idea is that so we create the logical state right here, we measure it using state tomography. But that's just to assess the state. But throughout all, you know, you're always
okay,
working at the logical level here.
Okay, just for checking the state that you put in, you sort of have, yeah. But everything else can be done logically. Okay.
Yeah, everything else is at the logical level. Yeah.
Sorry, I've got a question here. Yes, so could you explain again why the measurement outcome of the stabilizer before and after the logical gate should be the same?
Well, it doesn't have to, but so let me say it. So it has to be the same. That's correct. You could make it another value other than +1, right? But it has to be the same just to make sure that you're still in the logical subspace that you want. So remember, the stabilizers define your logical subspace. So if you don't have states with the same stabilizer parity going in and out, an error has surely happened.
Yeah. I mean, is this the reason? The reason of this situation is that the stabilizer commute with the logical gate, right?
Yeah, precisely.
Oh, yeah, thank you.
Yeah, that's exactly it. All right. I'm worried that I'm gonna run out of time for the following part, which I think might be a bit more interesting for you. So I'm gonna try to quickly go through this one. Yeah, the last thing we did was perform repeated error detection. So disclaimer: this had been done before in this paper, like Quaylin said in the Walraff paper right here, and it also had been done, very similarly in the Google paper in 21. That's how we just wanted to see how we fared against those results. So again, we initialize a logical state and you just measure a bunch of stabilizers, right? And you keep all your data until you find an error. And then you measure in your logical basis, you get a logical expectation value. You do that over many rounds, and then you can fit a logical error rate per round. So how did we do there? Well, this is what happens. So we went all the way to 15 cycles of error detection. We can't do more because the probability for you finding an error after each stabilizer measurement is quite high. It's 45%. So we're post-selecting quite heavily on our data. So at some point, it would take you a very large amount of time for you to get statistically relevant data for this plot. That said, the mean logical error rate per round is about 0.4% for all the states right here, which is pretty good. That said, this is you can't compare this to the recent error correction results because this is a much easier experiment, so to say. So yeah, no questions here. Then let's talk about upgrading to a quantum error correction chip. So when you go from quantum error detection to error correction, you go from a distance 2 code to a distance 3 code. So this code has 7 qubits. It's called surface 7. We're now going to do a surface 17 code. The price to pay for this higher protection is a price in complexity. You go from 7 qubits to 17, and you go from a 5 by 5 millimeter tube to a 10 by 10. That adds more packaging requirements. It also has a lot more control lines. You go from 18 to 40 control lines, so your fridge also gets a lot more complex. And you go from 8 cubic gates to 24, so the number of parameters that you have to calibrate also explodes, really. So having done that, maybe one question that you guys might have is what's typical operating errors for a device like this? And this is what we have right here. So we have about 10 to the -3 errors for single qubit gates. They're fairly uniform except for one of the qubits right here, which has to contend with the 2-level system. 2 qubit gate errors are about 2% on average, as well as readout errors on this device. In general, errors are uniform apart from some sporadic cases where you have a spurious 2-level system that's messing up your operation, really. And again, I should point out that this has been done in 2022 first time by the Walraff group, and ever since by the Google group, now 2 times with the distance 5 and the distance 7 code. So how do we do error correction, and how do we think about it? Maybe the first thing we can think about is what can go wrong when we're measuring stabilizers, right? So one of the errors that can happen is you may assign the wrong parity, right? So you input your data qubits in a certain parity state, but for whatever reason, your outcome of your measurement is wrong. And you can assess this sort of experiment by inputting different computational states and see, what's the error between the result that you would expect from the ideal. Another type of error that you can have is a non-projective stabilizer measurement. That is, you do your measurement, the outcome is correct, but you project your data qubits into a different state from your outcome right here. So these are the sort of errors that we'll get to see, but what we want to do is identify the qubit or errors that originate this, right? And so how do we identify them? So the main idea is that different syndrome measurements, so different physical errors have different syndrome measurement signatures, right? And maybe let me first define what a syndrome measurement is, right? So when you do a parity check, you typically get a measurement outcomes, right? And you could think, okay, these measurement outcomes are directly parities, but not quite, right? Because the way this whole circuit works is if your data qubits right here are in an even parity state, then the state of your NCL will stay the same. If not, it will flip, right? So for instance, when you go from, when you have a qubit error right here and you go from an even parity subspace to an odd parity subspace, what happens to your measurement results is that they're gonna oscillate, ideally, right? So here you have even parity and here you have odd parity, right? So to get stabilizer parity values, what you wanna do is basically do the XOR of this trace, and that gives you the parity outcome. But even that is not the quantity that we want, because we want a quantity that signals an error event, right? And basically what signals an error event is changes in parity, right? And this is what we call defects, right? So we're gonna see that different error mechanisms have different defect correlations. Perhaps the first thing to start with is errors on the same stabilizer. So for instance, if an ancilla error occurs, right, and I mean a real ancilla error, not a measurement error right here, what's gonna happen to your measurement outcomes is you're just gonna go from, if you're in an even parity, from one state that's constant to a single change to another state that's constant. If we see how that translates into syndrome measurements, into defects, it basically translates into two back-to-back defects. So 2 defects that are spaced by 1 in time. Okay. So we can pick these sort of syndromes by looking at what's called the PIJ matrix. So basically, this is just a measure of correlation between these syndrome measurements right here. So they tell you the probability of a syndrome happening at round I simultaneously with a syndrome defect happening at round J right here. And like we said, for measurement errors, these are going to be back-to-back. So for ancilla errors, these are going to be back-to-back defects. So they're basically all the rows in this matrix that are in the first diagonal. Now, if you have a measurement error, typically what occurs is you're in a whatever parity subspace. You get an outcome that's different, but then you go back to reading your state correctly. And this basically generates two defects that are spaced by 2 in time. So in this PIJ matrix, right, it's the probabilities that show up in this second diagonal right here. Okay. So already from a certain, just a measurement like this, you can get an idea, and this is real data right here, of your overall probability of getting an error. And this is just the probability of you measuring one syndrome at any given round. For this is a measurement of a weight 4 stabilizer measurement. It's about 20%. From those, excuse me, 10% are general ancilla flips, so general ancilla errors, and a much lower probability are due to measurement errors right here.
Okay.
Yeah. Any questions on this slide?
Yes. I read the paper. They speak about the sort of the syndrome element, the average syndrome element. My understanding is that you measure the average of the parity, because if the parity does change, your average will go down, right? So that will sort of that will give an idea like how much error that happened. And
so that's what we call here the defect rate.
Sure. And that's just an indication how good your physical qubit is, right?
Right, correct.
I see. There's nothing with a logical qubit. This is just the property of physical qubit. Is that correct?
Yeah.
Well,
but that's an interesting point. So if you read the recent Google paper, you can see that there's actually a 1-to-1 mapping of the defect rate of your stabilizers and your logical error rate, which is not surprising, but still very interesting.
Okay. The second question is that why is you just point out this curve defect rate? Why is the first point so high? Usually it's more long. It go higher. But this one,
yeah, good point. So if you see here in this measurement, we start with all our qubits in a product state of zeros. This is not an eigenstate of the X stabilizer that we're measuring here. So the first measurement outcome will be random. And that's why this first point is 0.5.
Okay.
Because you can likely land with the same probability on the even or odd parity subspace.
Okay. I see. Yeah.
Yeah, it's a good catch.
Yeah. All right. Okay. That's my question. Yeah. Okay.
All right. So we can think of other physical error mechanisms and how they impact these rates. So far, we've only considered qubit errors, but we know that we're dealing with nonlinear harmonic oscillator, well, sort of harmonic oscillators, right? So there's higher states that you can leak to, right? So there's the second, third, and so on states, and these are not these sort of errors are not caught by the stabilizer formalism, right? So these are not qubit-like errors. So you can't expect a consistent syndrome signature from them. But then what can you expect? Well, one way you can think about this is that when a leakage event happens at a certain round in your error correction experiment, you leak to this higher state, let's say the 2, and you can stay there for many rounds because these measurements are not necessarily, projective onto the qubit state anymore, onto the qubit subspace anymore, and the qubit subspace and the physical qubit subspaces. So you can be generating defects for many rounds until you go back to your qubit subspace, and then you might get detected as a qubit error, and then things go well again. So the way to think about leakage is that first is they'll give you a rise in error rates because in general leakage can accumulate. It's not projected back into the computational subspace. So you'll see defect rates that increase in time. And the second feature is that it'll give you large correlations in time between defects. And in these PIJ matrices, this was shown first by Google, it means that basically you won't just see high probabilities in the first diagonals, but you may see high probabilities into, the more distant diagonals that basically correlate between longer, further apart rounds. So to combat this, a useful tool is leakage reduction units, and I can go into details about our leakage reduction unit. I don't have any slides here explaining it. Only backup slides if you want to learn more about it. But what we do is we implement leakage reduction units in the qubits that we know are most vulnerable to leakage. In this experiment, two of the data qubits basically, and then we can measure second excited state populations, after many rounds of stabilizer measurements, and we see that by using an LRU, we can effectively keep leakage low in our both our data qubits and our ancilla qubits. So if you go back to looking at defect rates and PIJ matrices, you see that with the LRU, our defect rates become more constant, right? So they become flatter, and you start losing these long-term correlations. These start becoming much less likely because you're keeping leakage at a much lower level in your experiment. So yeah, so far we've only talked about identifying qubit errors in our ancilla, right? And through a single stabilizer measurement. But what if you want to detect errors in your data qubits, right? So in general, detecting errors in your data qubits requires multiple stabilizers. And we can start looking at what happens when that occurs, for instance, in the surface code. So for the qubits right here in the middle, what you'll see is that if there's an error here, it will likely trigger the adjacent stabilizers. Same for this qubit and same for this qubit, right? And the errors, depending on where they happen in time, can be either detected in the same round of error correction. So for instance, if an error happens in between your measurements on this data qubit D5 right here, it will propagate through DZ on this ancilla measurement and on this one in the same round. So what you'll get is correlations in space instead. By space, I mean space in your code. So you'll get two stabilizers. In here, this is the X2 and the X3 stabilizers that are correlated within the same round. Some errors, if they happen in between the two CZs of adjacent parity checks, are correlated both in space because they'll be detected by different stabilizers, but also by one length in time because this error just missed this CZ and will only be detected in the next parity check. So in this PIJ matrix right here, this will be in the first diagonal of this. So if you put all of these stabilizers together, what you'll find is that if you don't restrict your analysis to only a single stabilizer, and now you include correlations between all stabilizers, these diagonals right here will reveal errors within specific data qubits. These data qubits right here in the middle. But you may ask, and I think Quaylen asked this question before, what happens to qubits on the boundary of the code, right? These are qubits that are here and here, right? Because these qubits are only checked by one stabilizer, at least one of the X-type stabilizers in this experiment, right? Well, the answer is it kind of doesn't matter. So first of all, they will only generate one defect. That's important. So you won't see their signature as two defects as is usual. And of course, if an error happens, for instance, if this stabilizer triggers, right, you know that the error either happened on this qubit or on this qubit, right? Let's say it happened on this qubit. Well, your correction, has a 50% chance of guessing the error right. If it guesses right, you go back to your previous state. That's okay. If it guesses wrong and it tries to do the correction on this qubit instead, then what you end up is with an operation that's ZZ. But ZZ is precisely a stabilizer of your code. Right here, it's the stabilizer in gray. And you know that your logical qubit state commutes with your stabilizer. So doing a ZZ effectively does nothing to your qubit. A way to see that is by looking at what happens to your logical operator. If you do Z here, you change your logical operator twice. So effectively, nothing happens. So either your correction fixes the error or it performs a stabilizer. Both of them are fine, and it doesn't matter.
Yeah. Okay. A few things I want to clarify in this diagram. So in the figure D, A, B, C, D, the smaller one, the S arrow and the ST arrow, what does that stand? S arrow and the ST.
All right. So that's a good point.
Yes,
so
yes.
S stands for space error, space-like error.
Okay.
And ST stands for space-time error. So it's an error that's happens, distanced by one in space and also by one in time, which is why they're not on the main diagonal right here, but on the second diagonal.
Yeah. The second question is, I just want to understand this diagram. So what does this color represent? The color bar, is it a PI?
Oh, right.
Yeah.
So Pij is literally the probability of these two syndromes happening at the same time.
Okay. I see.
So it's really just the probability of this error event. So the idea here is that you're going to use this information later on to tune your decoder to guess better which errors happen based on your syndrome signatures.
Okay, so to know this probability is basically probably measure the average syndrome element. This kind of thing, right?
Yeah, exactly.
I see. Okay.
So you just have to dig around in your syndromes for correlations, and these different error signatures are gonna pop out.
Sure. The final question is that still in the figure D, you have two colors. And these two colors just correspond to the figure B. It has a Z arrow, which has this kind of color, and the X arrow has a different kind of color. I see. Okay.
Yeah. So this is just to allude to the different errors that happen in this figure.
I see. Okay. Interesting. Good to know. Thanks. That saved me a lot of time to read this paper. All right.
No worries.
Okay. Thanks. Okay.
All right. Any other question here? No? Let's keep going. So all right. So far we've learned that the different qubit errors leave different signatures in our syndromes. So how do we actually go about correcting errors, right? So the first point to make is that there's you can prove by a theorem that if you have correct for both Z and X errors separately, you can effectively correct for all errors in your logical qubit. And that's an important fact. And that's why in these experiments, I'm only showing one type stabilizers right here. I'm just saying, hey, we're going to look at Z-type stabilizers, and those are going to correct for X-type errors. The other stabilizers are going to correct for the other type of error, and it can be done, the analysis can be done parallelly and independently. That's not guaranteed that it's the most optimal way of doing things, but it can certainly be done independently. Right? So what we get out of an error correction experiment typically is a graph of points, right? Each point is a measurement round of a syndrome in time and also in space, right? So the space is the different stabilizers right here. Okay. Whenever there's a defect, there's basically a point on that graph. And what your decoder has to do is figure out, okay, how can I start matching these points right here to try to figure out what's the most probable group of errors that occurred with a certain landscape right here. Right? So the decoding problem can literally be translated into the problem of matching defects on a graph, right? So there's many different ways to tackle this issue. The most popular is known as the minimum weight perfect matching problem. This is a problem that's very well studied in math. And like I said, qubit errors always come into either a single defect or a pair of them. And the way you can solve for this graph is, all right, we look at these correlations that we showed earlier in the Pij matrix, and we can pretty much find, the probability for certain edges to appear in this graph, right? So then you can assign each of those edges a weight, right? A very rare edge, a very rare event, an error that occurs very, very rarely, has a very high weight in this problem. And the error that occurs much more often, say for instance, this ancilla error right here, has a very low weight. So what you want to find is the configuration of edges in this graph that gives you the lowest weight, hence the name of this problem, minimum weight perfect matching. And this is basically how you do it. So there's algorithms that are very efficient at solving this problem, and they're efficient enough that you can run them in real time, parallel to your error correction. That said, this is not the only way of solving this problem. One way that's very popular and that gives probably the best results is these neural networks approach, which is basically just a black box optimization of your error rates. But yeah, that's how your decoding takes place. Any question here? All right. If not, we'll move on to the last experiment. Oh, forgive me. There's something here. So the final experiment is just showing this in a prototype experiment of a distance 3 surface code. So we're going to try to correct for X-type errors in a distance 3 surface code. The reason why we're only doing X-type is because we couldn't do all X-type stabilizers with very good performance. So we're just gonna work with Z stabilizers. So in theory, we're not really protecting against all quantum errors. We're only protecting against one error. That said, we can still see what emulate the performance of a fully protected surface code by putting together, by looking at the superposition of states of your logical qubit state. These are basically 16 states. They're labeled right here. all the different combinations of these superpositions. We can prepare them individually, run them through this error correction procedure. We also do a logical operation to make sure that we're averaging also over the state 0 and 1 right here. We do a bunch of error correction rounds. We measure the logical operator of the qubit, and then we try to fit a logical error rate per round to a fidelity of your logical qubit versus the number of rounds. And in the end is what we get. We get about 5% logical error rate per round. Mind you, these are very consistent across all the logical state superpositions. And yeah, that's a logical qubit protected against X-type bit flip errors.
Sorry, right. the F arrow here just either the X arrow or Z arrow. Is that correct? The fidelity for these two gates, is it correct?
Yes, so we're only doing Z-type stabilizer, so we're only correcting against X-type errors.
Sure. Okay. So this is the fidelity for this logical gate. That's what I'm.
But this is the fidelity of this logical memory experiment. So we're just putting in a state and seeing how well it's preserved. Mm-hmm. This is similar to the experiments that were done by the Walraff group, with the caveat that we're only protecting against one type of errors, and for instance the Google experiments as well.
Okay. I think it's fine.
Sorry, in the other experiments, they protect for, like, they correct for both types of errors?
Yeah, that's correct.
Oh, okay.
Yeah, in the other experiments, they can so they have all stabilizers being measured. They can directly project into this state, and then you, like I said, you can run your decoder separately for different types of errors if you so choose to do it.
Yeah. Okay. Thanks.
Oh, sorry. Another question is that, so this logical fidelity here is the logical state after the error correction. You did it.
Right.
Okay.
Right.
I see.
You do n number of rounds, and then you measure your logical qubit right here.
Mm-hmm.
You correct based on, your syndrome measurements, and you average over many repetitions.
Okay. So it's not just use the logical state without error correction. It does correct it and then do the fidelity check.
Right.
I see. Okay. All right. Thanks. Okay. I see.
Right.
Okay.
All right. If there's no more questions, then I guess we're on to the summary. Again, two surface codes have been shown. In the first one, we had a distance 2 surface code where we initialized, measured, and operated a logical qubit. In the second experiment, we tried to run a distance 3 surface code where we protected against one type of errors in our qubit. The general takeaways of this section is that different qubit errors have distinct syndrome signatures in stabilizer codes, and the way you go about correcting those errors is by trying to decode those signatures. And yeah, finally, we've shown correction of bit flip errors in this distance 3 surface code.
Okay, is that the final summary, or
yep, that's
okay,
all.
Yeah, okay. Thanks, George, for the excellent talk. It does help me to understand a step further, but I think still a lot to understand. I'll probably leave a question from other audience. Is any question that people want to ask?
Thank you for the nice talk. I just want to have two basic questions. The first one is, yeah, about the decoder. You mentioned that there are some approaches in the decoder. If you have the, like, for example, time and space errors, then if you do the MWPM or neural network decoder, does that mean that you cannot do the decoder real time? You can just do it at the end of the measurement and correct it? Because you have the different time errors, you must collect all the information at the end. Is that correct?
That's a great question. So in the experiments that I've shown, they were all done in the end offline, so not in real time. But in terms of minimum weight perfect matching, there's efficient algorithms to solve this problem, the problem of minimum weight perfect matching. For instance, one of them is the Blossom algorithm. That algorithm can be implemented in an FPGA, and you can try to make this guess or solve this problem as these rounds come to you. And in fact, I think there's been, I don't know if these, there's been experiments that have shown real-time decoders right now. I know the Google experiment and the Riverlane experiment together with Rigetti. I don't know if they used the Blossom algorithm, but they've certainly used other algorithms that, you know, are efficient enough that you can implement in an FPGA alongside your experiment.
I see. If it is alongside, if the error is correctly, then there's no problem. But if somehow the correction is wrong, will they propagate the error and they still can correct at the end?
Right. Yeah. Well, you can think, you know, some of these defects are only going to be matched to other defects in the future, right? But, you know, you can be solving that in real time and making, you know, different guesses as time goes on for some of these matches, right? What matters is after you've done your logical qubit measurement, what's the final configuration of matches? Because you know that, you know, as time goes on, there's very low probability that a defect here is going to match with something that's at the end, right? So as you're solving, you know that the important thing is just that you don't get a backlog of information and you're not solving it fast enough at each time that it comes. As long as you can do that fast enough, you can always make a different guess as time goes on.
I see. Thank you. So my another question is about, you said the leakage problem, if the error is leaked to higher state, like 2 state, then how to actually correct it? I didn't get that point.
Yeah. So that's a good point. So we don't. So the leakage reduction unit doesn't correct that error per se. What it does is it takes your leaked qubit and brings it back to the computational subspace. Now, the way that happens, it can create an error or not. You don't know. But if it does, the fact that you brought it back to your qubit subspace means that it's an error that your quantum error correction protocol can fix. And that's the key point, right? Because errors that are not in your qubit subspace cannot be fixed by error correction. So that's really the only thing that leakage reduction does. Yeah.
So you can identify it is in higher space. So that the first thing you have to do is you have to detect it or not.
You don't necessarily detect it. It's an operation that, so ideally, if your qubit is not in the leaked subspace, it will do nothing. And if it is in the leaked subspace, it will bring it back
Okay, I see. So it's automatically, you don't even know whether it leaked
Yeah,
and
you
come
don't.
back.
It doesn't signal the way we've implemented it. If you want more details, the implementation is in this paper right here. What I can tell you very quick, it's basically a Raman transition from your second excited state to your resonator, and that Raman transition only shuffles population if you have population in the second excited state to start with. If you have nothing, the pulse won't do anything.
I see. Okay. Okay, thank you very much. Thanks.
No worries. Thanks for the questions.
Yeah, thanks for the question. Any other questions? Yeah, since previous Minjian also asked, can you go to the next slide, because I think I just for identifying the error, this part. Maybe I'd like to not this one, maybe the previous one.
Maybe this
correct,
one.
Correction error. Sorry, correction of the error, which is after this.
This one.
Previous page.
Oh, previous. This one, decoding.
Yeah, sure. Can I understand what the bottom right chart? What is this? This color bar correspond to?
Oh, the color bars, right?
Yeah.
So these are basically,
yeah.
So if you remember the Pij matrices, this is literally the probabilities that you get from these lines.
Yeah. Okay.
Right. So for instance, a qubit, you know that errors in, certain qubits happen in this place in the probability, in the correlation
stabilizer
matrix.
Yeah. Okay.
So so these are errors that are defects that are spaced by a unit of space, right? Signaled here in red. So these happen with 2% on, the qubit that's in here. So for instance, these two, the edges that come up like this, these are just measurement errors. These again happen with 2%. For instance, what's interesting is from our, in this processor, the most occurring error is ancilla flips. So it's your ancilla is flipping state, and these happen with much higher probability, 4%, depending on which stabilizer you're looking at, but it can go up to 8%.
Okay, and Z1, Z2, Z3, Z4, they have different sort of diagram. How should I read this? It's very small though. I don't know.
Oh yeah, sorry. Yeah, this picture maybe is not great. I just wanted to show them as a spatial representation, but basically Z1 is the weight 2 here in the corner.
Okay.
Z2 is the weight 4. Z3 is the one here.
Oh, I see. Okay, I see. You highlighted with a little bit dense color.
Yeah, exactly.
Okay,
maybe not the best way of showing it.
That's okay. It's okay. Okay, got it. Yeah, I learned a lot. Thanks a lot. I mean,
no worries. It's a pleasure.
A lot of knowledge. Okay.
Yeah, that's good to hear.
Other, yeah, good, very good. Any other questions? Maybe for person who is the first time to listen to this topic, there are a lot of things to digest. For example, what is stabilizer? What is all this kind of? So I can understand, like, it's gonna be a little bit hard for person to listen.
I have a question.
Yeah. Okay, go ahead. Yeah.
Yeah, and I observed that the logical error is higher than the physical error. So it's like 0.5%. So we are expecting the error to go down to the 10 to the minus 12, right? So how we get around this? So this is kind of confusing. Yeah.
So you're right. We effectively made a logical qubit that's worse than our physical qubit. I think is your point, right? And that's true. So the underlying assumption of error correction is that and you won't see it in these results, of course. But the idea is that if you increase redundancy, that is, if you increase the size of your code right here, what we call distance, you can, provided you're below this threshold of errors, you can start, your error decreases exponentially. So you take a penalty that's quadratic in the number of qubits, right? Because it grows with the area of the code. But you get an exponential decrease of your logical error rate. And so
does that mean at this stage the error is still caused by the overhead? So we don't really get better than the physical qubit, and it will be better when we increase the distance in the future.
Yeah. The state-of-the-art results for now are the Google paper, at least when it comes to expanding a logical qubit. And I believe those are still in the 0.1% error margins. So we're still, there's still a lot of room for improvement.
Thank you.
Sure. So following this question, you actually mentioned a good point. So for the photonic qubit, they already passed the break-even point, right? For certain, they use the error correct qubit compared to the best, which is 0 and 1, the harmonic state. They already passed the threshold. But for this service code, that it hasn't reached that point yet, right? So okay. And
well, no, I'm not sure. So that comparison is a bit tricky to make because they're not exactly referring to the same construct. So in a bosonic state, whether you're using CAT states or GKP states, right? So I think for the break-even, beyond break-even result, they were using GKP states. So what you're taking is, you're saying, I have a physical qubit, that's my Fox state, I believe.
Yes, 0 and 1, yeah.
And I'm comparing the performance of not many qubits together.
Yeah.
But, one different way of encoding, a harmonic oscillator state, which is this GKP state, right?
Yes.
So it doesn't map directly to what's here, right? So beyond break-even in that context is a little bit different, and in my opinion, a lot easier. And I think that would be a general remark.
Yeah, they have difficulty to, for example, upscale because one cavity is equivalent to one logical qubit in a sense, but you need to have many. That's my understanding. Unless you do it 2D, otherwise for 3D cavity, that's
right.
Yeah.
But even with that, it's just a different way of doing quantum error correction.
Sure. I remember Max is doing in this direction. Yeah.
Max is working on GKP state. Yeah.
Yes. So yeah, really nice. Any other question? Okay, if not, I want to thank George again for this excellent sharing about his experiments and the knowledge. I do feel this is a very hard field. It's been going on by Google a lot. So I think do hope if you ever come to visit Taiwan, do visit us. I know Will is coming to Taiwan quite often, so you too.
Interesting.
Hopefully, I can also learn about your new result, new progress in the Physonian multiple qubit, which is quite interesting when you show me as well.
Yeah. Hopefully, I'll have some stories to tell on that. Yeah, thank you a lot for having me. It's been a pleasure.
Thank you for spending this night time with us. Yeah. So okay,
no problem.
Keep in touch. Hope to see you very soon.